developed a Harry Potter themed potions class for the honors college.
You actually went with your little beaker or whatever to the
Yes.
roof of the building. Hi, and welcome to this episode of Under the Microscope, your science podcast spotlighting materials and nanoscience. My name is Svenja Lohmann. I'm your host for today, and with me we have a special guest, Chris Brewer, who is a postdoc at the University of Texas in Dallas, USA. Welcome, Chris. How are you this morning for you?
Hi, I'm doing well, and thank you for having me. I'm looking forward to being here.
We are very excited to hear about your science and your scientific journey. So let's start straight away. Would you explain your research to me and to the listeners in very simple words, please?
I've worked in a couple of different labs, so my research has ranged from organic synthesis to surface science. So long ago, as an undergraduate, I synthesized azide molecules that were used as molecular linkers with the goal of being able to do click chemistry in vivo for building molecules. As a graduate student, I synthesized organometallic precursors, usually for either photo-assisted chemical vapor deposition or electron beam induced deposition processes. And for there, I also did studies where I looked at how the molecules interact with different conditions like light, because when doing a deposition process, you need to break the molecule apart to be able to form your layer. So as a graduate student, I developed methods to investigate and determine the mechanisms for how molecules break apart under light. As a postdoc when I was at NC State, I synthesized new chromophores for OLEDs to try and make some organic ones that were, fully organic, not organometallic, but also having properties that would be suitable for devices. And now, moving to UT Dallas, I've transitioned from synthesis to surface science, and I am looking at techniques for depositing tin sulfide and iron sulfide onto self-assembled monolayers. Basically, look at a model system of how we can do this onto an organic phase.
Okay, so that's a lot.
Hopefully, I remained brief.
Yeah, some questions. So you already mentioned, I think, LED applications. So what is your research more, fundamental research based, or is it more into an applied direction? What would you say?
So my previous postdoc, when I was working on making the OLED chromophores, a hybrid, I was doing the design phase and the fundamental part to test out different designs of the molecule. So that part, I was just kind of making new molecules to see if I change this about the molecule, what does it do to the properties?
Mm-hmm.
And so that part, there's a fundamental aspect to it. But the end goal there was, once I made one that was suitable, I handed it off to our collaborator to fabricate into an OLED to see if it was suitable. So it was kind of an accelerated fundamental approach where once it looked good, we handed it off and, just to see how suitable is it.
Okay, so you were in the fundamental side, and then you had kind of a partner who was working on the application side, and through close correlation, you can kind of speed up the fundamental to potential application side?
Well, I could get an answer to whether or not what I think is, how I think it's working in a reaction flask and solution is going to is also true if it's going to behave when it gets on the surface in a device. Now, my current work is more on a fundamental level. So we are we look at substrates that are more, kind of like the size of the end of my pinky there. And we're using small systems so that way we have a lot of control, because so we're not doing like vapor deposition techniques. We're doing chemical bath deposition, which is out of the solution phase. So this is used, you can find it used in industry in very large scales, but that's of course large, expensive reactors that have a team that know how to use them and manage and control the properties. But here I'm doing it on the small system because I can control that in the lab, and it's something that I can use that system, really understand every component. So my current work is much more on the fundamental side.
Okay, interesting. Just because you mentioned it, and I don't, sorry, I'm a physicist actually by training, but I have not a lot of chemistry background. Chemical bath deposition. Can you give me like a introduction for dummies, very brief?
So it's still a deposition technique where the goal is to deposit a material onto a substrate. But chemical bath, actually, it's kind of just like you're thinking in the words. It is a chemical bath, like it's literally a beaker with a solution where you mix your metal precursors and then your different sources for you mix your source for your metal, and then different complexing agents and different reagents in there that have some of to incorporate the different elements that you want into your material. And here you're looking at more of the kinetics of how these things react in order to get the right reaction to occur in the solution and have it deposit onto the surface. So it's as simple as it sounds, where it's a deposition being done in a beaker. You don't have like a traditional deposition system where you have large vacuum chambers, like where you've got to get the substrate in, pump it down. You prep your solutions and you add your substrates and you wait the appropriate time. Of course, there's more to it than just that. Because there's more to it than just that. But in the simplest terms, that's an overview.
Okay, thank you. I think there's always more to it, right? There's always a lot of details which we can't always, include on the podcast, and maybe too much for everyone. But that was a good first introduction.
And there's always a way to describe what you do that leaves out a lot of the story.
Yeah, I know. Okay, cool. So this is basically what you're doing now. You're using this chemical bath deposition to deposit which materials are you depositing?
So tin sulfide and iron sulfides.
Why tin and iron sulfides?
So both of them have known, they're good for photovoltaic applications, which we're trying to deposit them onto self-assembled monolayers that as a model system for being able to do this on other organic systems. So it kind of proof of concept level to show, this can be done and it can be applied to these organic systems, which would be popular for getting to flexible electronics. And when you start looking at organic systems, if you remember from when you took, I know you're a physicist, but you probably at least saw that we have different functional groups that we use in organic. You can pattern a substrate, and the idea is if we can get the deposition conditions right, we can get area selective deposition, which means that depending on what the end of your organic substrate looks like, you can functionalize it in a certain area, and hopefully you can tune the deposition conditions to only deposit in one spot. So that way, if we were going to use this in the future to fabricate a device, it wouldn't just go everywhere with no control. we could get it to pattern in a certain spot.
Mm-hmm.
So that's kind of, that's the long-term goal with what we're trying to do. And I think that reveals a little bit more of, there's more to the story there of tuning it and why we're doing these model systems in the form that we are.
Okay, thank you. Very interesting. Um, I understood now that you recently moved to the University of Dallas, if I understand correctly.
Yes, I've been here for about 1 month.
Oh, that's very recent.
So yeah, I'm still learning the ropes of my project a little bit. I'm there's a lot of pieces to learn right now.
Yeah, I can imagine that's a new group, new city, I guess, new techniques. But can you tell us a bit more about how you got there, basically? So what has been your career journey? What motivated you to become a scientist? How did you end up where you're now?
So long, long ago, if we look back to when I was in grade school, so this is back in the US high school, I volunteered at the Museum of Science and Industry in Tampa. And that was a little bit of my first exposure to the science education side. And after being a volunteer for a little bit, I joined in a research project that they had there about it was an informal education project about how families learn in museums. So we're looking at developing scaffolding strategies to try and enhance the learning experience of families in the museum. That would be where I kind of started my research experience. So that was back me in 2008. And through those experiences, I also eventually started working as a employee doing science demonstrations and teaching summer camps at the museum. So that experience got me interested in science education. And I continued working there off and on after I had left Tampa to go to my undergraduate studies at Florida State University. So that was in Tallahassee, Florida. At Christmas time and summer, I would return and continue working at the museum. When I was at FSU, I was a chemistry. Well, I had many different majors. I was one of those that switched. Where I finally landed during my fourth year is when my major was finally set in stone, was chemistry and biochemistry. The biochemistry part comes from I had just taken all of the electives that also satisfied that, but more of the organic and inorganic chemistry is where I was interested. So while I was at FSU, I also did undergraduate research. So that was my first kind of dive into the discovery side of being in the wet lab, of beyond just you take the course and follow the recipe in the book and you get the exact product that they tell you you're supposed to. That was kind of where I started having the opportunity to explore and be curious in the lab. So I worked with Professor Lei Zhu. My main project was making these bis-azide molecules that would serve as linkers in biological systems.
Mm-hmm.
And while I was at FSU, I also continued looking at my interest in science education, where I kind of by luck, I picked up a job that I was in charge of all the demonstrations on campus, or not campus, for the chemistry department. I was preparing, I would coordinate with the faculty and prep all this stuff for their classes. Some of them I just hand them materials. Some of them I join in their class and do the demonstration for them. And then, so I'd come in and I would get to bring my card in and be the exciting guy in the classes there.
Sounds very fun.
It was a lot of fun. It was a very fun job that you might never find one of those. You might not ever find one like that again. But I'm glad I did it for a while. And then I continued my education experience by going to University of Florida for graduate school. So that's in Gainesville, Florida. So yeah, that up until now we're still in Florida for my whole life, but I've had a lot of good experiences there, and I'm very happy with how I've what's led me to where I am now. So while at UF, I I worked with Professor Lisa Mackley-White, who she's also joined you guys on the podcast. I think it was a couple months ago.
Yeah, I think beginning of the year.
Yeah, so I worked with her. That's where I worked on my project with designing the mostly ruthenium molecules for photo-assisted chemical vapor deposition and electron beam induced processes. And I also explored some of my interest. I continued to explore some of my interest in science education while I was at UF. And one of the things that I did was I developed a Harry Potter themed potions class for the Honors College. And actually I've been lucky enough to been able to return to UF. The Honors College has invited me back a couple of times to help run the program after I've left. So I've been very happy to see it continue to succeed for years after I've left the university. But that was a lot of fun.
Can you give me one example? What was one Harry Potter themed? I don't know.
So we had a lot of experiments, and actually it kind of developed into an interdisciplinary class, which was fun because I got the opportunity to get to know a lot of people all over campus and get to know a lot more of the resources that were at UF. So we had one professor who was down at the med school, but she had a biology and a history background. So she was Professor Sprout, and she would join us at the gardens that were at UF, Wilmot Gardens, and we would do herbology class there. And then up in the teaching lab, I would do experiments like for our Lumos spell, we would make glow sticks from scratch. Me being, trained as an organic chemist traditionally, of course I had to throw in the small organic synthesis into the course, but all the students were able to do it. We do some other stuff, like our one of our alchemy experiments is we synthesize and extract dyes from either we use some different chemicals to make Prussian blue or mauve, or we use cochineal insects to extract out the carminic acid. So that's one of our alchemy experiments, and we make these dyes, and then the students get to make their own tie-dye t-shirts using the dyes that they made, and they actually turn out pretty cool. Those are just some of the experiments. We try our best to mimic, to use all the spells that we can, but of course we can only get it so close.
Sounds magical.
It usually does.
Cool. That sounds very nice. Where were we before I stopped you there?
So UF, I had developed the courses and I had done, I'd gotten more research experience. So how I got to where I am today was my main project was looking at photo-assisted chemical vapor deposition. And that was a collaborative project between Lisa's lab at UF and Professor Amy Walker at UT Dallas. So at the end of my graduate career, I was able to travel out to UT Dallas and get some experience with the depositions. And that's where I got to know Amy a little bit better. And I enjoyed the material science side of the project. So I found myself getting a little bit more interested in the surface science. And so that was right before graduation. And then I went to do my first postdoc at NC State, working with Professor Phil Castellano. And there, my main project was doing synthesis of organic chromophores for OLED applications. But when the funding was up, it just so happened that the timing of everything worked out just right. My former collaborator, Amy, was also looking for a postdoc to join for the chemical bath deposition project. So everything kind of timed right, and now I'm here.
Wow, that's been quite a few places also you've done research in 3 different states, right?
Three different states. I forgot in between FSU and UF, I was at University of South Florida for a little bit doing sugar chemistry. And it was an enjoyable experience. That was for summer REU. One of the most important things I learned from that experience is I do not want to do sugar chemistry. But it was fun to learn. It was fun to learn a new technique and learn, get involved into a new field for a couple months.
Yeah, and I guess it's sometimes knowing what you don't want to do is also,
It narrows things down a lot. It does help you because you can at least look at something and say no.
Yeah, that's a valuable skill, I think.
Yes.
I think this sounded like quite an interesting journey, and I'm very impressed actually by the museum where you worked. They just employed you, even you were still in school, right? So
yes. So I started there as a volunteer at 14. I started working on the research project when I was 16, and I was between volunteering and employment, I was off and on there for about 10 years.
That's a long time.
Not consistent. There were large spots of it where I was absent because I was in school.
It's very cool. It's a very unique entrance, I guess, into science, or a very nice program.
It was definitely, it's definitely different than your traditional classroom. It was fun. I wouldn't trade, that kind of way of being introduced to science through science education for anything. I'm happy with where it's gotten me.
When you go a new place, do you check out other science museums?
Sometimes. I'm better about doing that stuff when I'm traveling to somewhere as a tourist than when I live there permanently. When you live somewhere, you don't really explore around like you're a tourist, but when you're somewhere for a short time, you look at the map and you decide, okay, well, I'm only here for 3 days. What am I going to hit? Because I don't know if I'm coming back. When you live here at home, you look at the map, you drive by the place every day, say, I'll get there one day. So when I travel, I like to check out some of the science institutions. I'm a lot better about doing it there than where I live.
Yeah, I think we all have this problem that we never are a tourist at home, so to say. Yeah. So now we heard from a lot of places you've been already, and you already mentioned quite a bit of different research projects you've been involved in. And on this podcast, we have a section which we call In Other Words, where we ask our guests to just pick like their most fun or their most quirky or their favorite research project and explain it to us in simple words, as always, because not all our listeners are scientists. So can you pick one and explain it to us, please?
If I had to pick one I was probably most proud of and that I enjoy telling the story about the most, the second major project that I had when I was in graduate school, it was looking at, just like my first one, it was like looking at ruthenium molecules for photoassisted chemical vapor deposition. But here I picked the molecules out and I showed them to Lisa and asked, how about we try these? And she said, sure, looks good. What I had done in this project was I took the lessons that we learned from the first batch of precursors that we did deposition on. And the way that, since we're looking at in simple words, the way that this deposition works is you make a molecule, and I would ship it over to UT Dallas so that way Amy and her graduate students could look at the deposition. You, under vacuum, are pulling it into a chamber. And once it's in the chamber, you have substrates here, and then you have light that's shining over it, like in that direction. And the precursors are interacting with the substrate they're interacting with the light before they hit the substrate. Ideally, the molecule should interact with the light, and this will excite them. And what we want to happen when these molecules get excited is for decomposition to start to occur. So we want them to lose ligands upon excitation. And that way we have a more reactive intermediate that will lay down on the surface, and it should undergo subsequent reactions. And then that way we can form a metallized film that won't have incorporation of the ligands that I need that were there on the molecule. So my part of the project was investigating how they decompose. Because what I needed to understand on my end was what pathways do these molecules go when they decompose, and how efficiently is this done? Mm-hmm. So basically we're looking at mechanism and quantum yield. So quantum yield is a measure of, basically it's like a percent yield for how many events of decomposition am I getting for in each photon that I put in. When I first joined the lab, one of the first things I had to do was figure out what equipment do we need to buy to determine these quantum yields. So I was able to design the system. So the experiment really felt like it was my own. Mm-hmm. You know, all the problems that it had were also my own, which so I was responsible for that too. But it felt like I really had a sense of ownership over that, and then I developed a method to where I could use just IR, so infrared spectroscopy, to look at the solution, and from there I could figure out exactly what products are being formed when you shine the molecules of light, and from there I could also use that to determine how much decomposition is occurring. So I was able to get that information, and I was able to figure out through some of those experiments, the stepwise process of how do we go from the fully intact precursor all the way down to how products that I can't detect, that I can no longer spectroscopically detect, because once you pop off every ligand, you lose your spectroscopic handles. So there isn't something that if I had carbonyl ligands that were on there. So once you've popped off all three of them, there's nothing on the molecule left for me to see in the IR. So, I was able to push it as far as I could, but I was able to get multiple steps and basically understand the full decomposition pathways of it. So that's a project I'm probably most proud of. Okay. And I enjoy the story because, that one, it was a long journey to get the answer. Mm-hmm. And once, you have that moment where you felt like you figured it out, it's pretty exciting.
But you found a final working precursor in the end, or is it still ongoing?
What I would do is I would design the precursor, I would synthesize them, and then I would screen them for suitability by looking at the mechanism for decomposition. I need to make sure that it will decompose with light. Mm-hmm. And I want to see if I can push it, to get as many of the ligands off as I can with light exposure. So that way in the surface system, it's a good probability that we can get rid of all the ligands. Mm-hmm. And then I was also screening them for high quantum yield values, because the higher the quantum yield, the more efficient the process is. And that means in the deposition experiment, you have a higher probability of it working. Mm-hmm. From the design parameters, that was our thought process. So basically, once I designed a couple molecules that I thought were suitable candidates, I would send them to our collaborator for trying out. So Amy's lab would give it a shot, and then they would let us know what worked, what didn't, and we would use that to go from there for designing the next phase. Of course, there's time. It takes all the time to get the molecules to do depositions, to understand the data. So, it's not as fast as I send it to them. Yeah. And then next week we say, this isn't going to work. There's a lot more time in there, and a lot more, kind of stepwise growth on each ends to get to the right answer. So in my work, what I did in that particular project was determine molecules that were suitable candidates, and determined these ones could work but not as well. Here's from the library the ones that would probably be the best. That work is actually still underway on the deposition side to see how well my mark of suitability stands. Because once you get into the surface science world, it's different than doing it in the reaction flask.
Yeah. Isn't always.
Yeah.
Okay, so basically you have given recommendation, which you hope is very good, but it's still, you still need to see if this is true.
Yeah, so that's that was actually kind of a theme, and it's an overall theme in Lisa's lab. As a precursor design lab, what we did was we made molecules, and from the best of our abilities, with all the techniques that we had available to us, we would determine precursors for all the different techniques that we designed them for. Of this could be a suitable candidate. And based on what we know from previous molecules that have worked and how we've analyzed this one, we think it has a good probability of working. And those are the molecules that we would send out to people to try for different processes. Many times we got hits where it worked well. Every now and then, no, they did not. Because the story is always different. Every surface science experiment is different. When you get them in the gas phase, they might behave differently. So yeah, we do our best with the knowledge that we know to give you something we think will work.
So you have to kind of, how to say, have some tolerance for, maybe not working things. And I guess you always have to do this in science, right? There's a lot of things that are not working.
Yeah, and that's part of the fun of it. If we when something doesn't work, we figure out why, and then from there it is a learning experience. We do learn what about that precursor was a problem. Although it may not have worked for the deposition experiment, we learned a good bit about precursor design that we can't learn from just a bunch of analytical techniques. Knowing that it works or does not work in the in the Showtime experiment, that's a very important piece of information too.
Yeah, sounds good. So we talked a lot about your research now and your research experience, but being a scientist always, entails more than just standing in the lab.
Yes.
What are there aspects that you like about your job?
Well, every day is different. So you don't walk in and just do the same thing day in and day out. So I like that part. And the whole job is, problem solving. And it's, you have to think about it in the right way. So to me, I think about it's kind of like solving mysteries and puzzles, which are fun. It's not something you can just answer all of your questions in one day. But everything that you do, it's important to keep track of it. So, and the reason I mention that is, so in science, we're given kind of as a researcher, you're given just a project, and the project is, it's on a simplistic scale. You're told you need to deposit this material onto this surface, and we want it to be clean. Or on the synthesis scale, it's you make molecules for this application, or try and make this drug precursor or something like that. The projects you're given are they're very simple at the end of the day. Well, they're not simple to do, but the goal is it's a goal that you have. It's not, you're not given a laundry list as a project. If you need to check all these things, it'll be good for all this stuff. As you go, you learn a lot, and your own curiosity. I can test things, and I can take projects into directions that weren't initially the goal. but are still interesting, and we can learn more things from this. Little accidental observations can lead to very important and they can lead to very important discoveries. So, like, one example of that would be when I was a graduate student. I had one reaction that for the life of me I could not get it to work.
Mm-hmm.
I was struggling. I was trying different reagents. I was trying, heating it. And then one day I set the reaction up, went out to grab lunch, and I came back and it worked. But I hadn't actually started the reaction. All I did was put everything in the flask and walk away. I hadn't actually started it with heating. And through, I had a really tough time replicating it. So what I ended up having to do in that case was figure out that it was because it was a sunny day that day. And this was Florida summer, where in the afternoon, when I was setting up these experiments, most of the time it was stormy. This one particular day, it was sunny, and the sun was shining in through the window in the lab. And the light is what actually ended up making it work better than anything.
Okay,
and through
so you
that,
needed UV light or just any
sunlight.
light?
Sunlight. We tried replicating it with all of the lights that we had in the lab, all of the nice high-end UV lights, and we couldn't replicate it the same way. And because of that, I would set up my reactions, take them to the roof of the building, run them there, because that's where I could get the most direct sunlight.
So you actually went with your little beaker or whatever to the roof of the building. Okay, that's really funny.
So yeah, I had a key to the roof of the building, and I would take my reactions up there and let them run, and they worked great. So that's part of the fun part with science. The goal was I need to make these molecules.
Mm-hmm.
The struggle was making the molecules. The accident was I made them one day, and I couldn't figure it out how, and I tried to reproduce that, and then you get to do fun things like go up to the roof of the building and do your work. And the other, so that's kind of the aspect of you never know what's going to happen, but everything is important. So it's just one little thing that you do might be more significant than you think. And there was no method for that. There was no set procedure for you're going to need to take it up to the roof. That was all discovery, and you get to have fun with it and really create it your own. And while I was doing the other project I was describing earlier, there were molecules that I would decide that I want to make that other people in the lab would try and convince me that this isn't going to work. This isn't this isn't something you should do. But I wanted to, so I do it, and those molecules actually end up being exciting. So just because they weren't in the initial goal doesn't mean that it's not something you should also just give a shot and see what happens. So that's part of the part that I like about science is I like solving the puzzle. I like that it's a mystery that you don't know the answer to, but you have the tools to get your way to the answer. And I like that every day is different. So, I could know exactly what I think I want to do next week, experiment-wise. But I could see one little observation while I'm prepping my experiment that could tell me, it's not going to work right. Or I could see, there could be a color change. It could tell me something else is happening. And the plan has to change. You've got to adapt to it. So, that's the exciting part to me.
It definitely never gets boring.
No. Well, I'm sure that there are people who can find, the work can get boring, but to me, it's my curiosity that keeps it exciting. I like to, I'll get curious and I just try something. And, even if it doesn't work, I think I learned that.
Yeah.
Um, so for me, the curiosity is what keeps it exciting and not getting old.
I'm so glad that you're such a curiosity-driven person, and I wish you many more, how to say, lucky accidents or
Well,
I don't know, things
you
that
never
happen
know.
and during while you grab your lunch, you come back and suddenly something works.
Sometimes serendipity is nice when it works. It's not the best to rely on.
No, no, but you figured it out in the end, so it all worked out, I guess.
And of course, it's a long journey to get to the end of the project. It's not, some of these things, it takes multiple years to solve the problem. It's not always, sunshine and smiles in the middle of it, but you pull through it.
Mhm. This is actually a very good turn to my next question, because my next question is, let's say, a bit more about. So now we talked about what you liked about being in science. Now I would like to go to things that are maybe not so great, or maybe more things that you want to improve. And we always ask our guests if they had 3 wishes, what they would ask for.
Okay. So the part I don't like, it can be very frustrating. Just like, the part I like is that you're doing the problem solving and it's kind of like, you're solving the mystery. I like that aspect equally as much as I don't, because there are questions you have about your system that you can't find the answer to because someone else has not done it. Otherwise, there's not a reason for you to do it. You're doing things that other people haven't. So that when you get stuck, in that time frame, when you're doing the trial and error, when you're sitting there just, at your desk, working out stuff on paper, trying to figure out what's going on, it's very frustrating when you don't know. And so that would be the part I don't like,
Mm-hmm.
is, that feeling of frustration. Now, if I could have 3 wishes to make, the experience more fun, of course I'm going to wish for as much as I can. But one thing that is not a surprise is the scientific tools that we use come with a big price tag.
Mm-hmm.
So you can read about all these tools in literature that people use. You can read about them in textbooks of, oh, you can use all these different analytical techniques. But when you were at your lab in your university, you have what's available, because this is the suite of instruments that your lab has needed in the past. This is the suite of instruments that we've had, your university has had funding for, and most people see the highest usage of.
Mm-hmm.
Um, but when there's instruments that you don't have access to, and you're curious, maybe this might help. It's not as easy just to do a quick little one-off experiment or design an experiment around a tool that you don't have.
Mm-hmm.
So I guess wish one would be, just access to any tool you want. Um, Now that being said,
Mm-hmm.
most places you can get a lot of information from the tools that are available. But it'd be fun to just have any tool you want at your disposal well, not at disposal, but at your availability to
Mm-hmm.
use. So one of the other things that, keeping kind of on a tool aspect, for me, I would like to have through graduate school, I didn't realize how helpful it would be, but having a better working understanding of how the tools in the machine shop work, and being able to do those kind of skills myself
Mm-hmm.
would, I think there'd be a lot of help for in my work, because if I get an idea on designing something for an experiment, I would know the limitations of what the tools that people use to build things are, and I could use that in order to design custom setups But if I had the ability to use those tools myself, of course I can touch them and use them, but I don't know how to do any of it properly. I don't
Mm-hmm.
have that skill. So, but if I had those skills, I could take it from idea to go design something that would make this easier. And I think I could come up with some pretty cool stuff for in my experiments. It would, it'd be fun to do all your own like custom setups. Like, well, if you're doing like a deposition experiment, everything's in home built stuff, all
Mm-hmm.
stuff designed perfectly for that. But, that being said, you can do a lot with the materials that you already have. You can do a lot with traditionally commercially available materials. You don't always need the custom setup. For me, that would be fun because I like to tinker with stuff. And I guess the third one thing I've seen that's been getting more popular is some of the robotics and the chemistry. And I think there's a lot of usage for some of that for being able to explore your ideas. So when you're at like the postdoc or the graduate student level, if you're able to incorporate some like the robotics to prepare solutions so that way, you could have a large array of them all done one way. Or so like in my case, if I could have it set up a couple of different, deposition techniques,
Mm-hmm.
then I focus my time on analyzing what's happened rather than preparing all the nitty gritty small steps. I can explore a lot more ideas faster. Now you do have the aspect of you would have to trust the robot to do it, to all the same way that you can with
Yeah.
your own will and hands. But for idea exploration, that would be kind of cool to have
Mm-hmm.
for in the synthesis lab. I know that's been it's kind of a newer tech. It's kind of a newer thing where you've got robots that can do the synthesis.
So this already exists in some labs, or
Yeah,
is this more of something that's still the
it
future?
it's growing, I think is the right word for it.
Mm-hmm.
There are labs that do high throughput synthesis with robotics, but some of these systems, they make sense on the large industrial scale. So for doing for like my application, probably involve like designing the system. So that's why it'd be a wish because I would want to design and program all that. If that just existed to make some of the routine stuff just kind of flow easier, and that way I just get an idea, punch in the conditions, and it starts, and then I can get like 3 or 4 ideas, try it. You don't have to weigh the options of, yeah, I could do all of these ideas, but then you look back behind it and say, well, but in order to accomplish these, that's a month or so that I'm off topic, not moving towards the forward goal.
Mm,
So
yeah,
that would be kind of a wish to help satisfy some of the curiosity.
might not might not be impossible, right? This last wish, if your site already exists, it might become, more cheaper and more readily available in the
Yeah,
future.
it definitely will. Right now, yeah, I mean, there's the price tag barrier. There's no way, no way that you'd want
I
to
think
spend
honestly,
a ton on it.
most answers in this category always comes down to time and money.
Yeah,
Okay, but very valid wishes. I hope they all come true. um,
maybe.
we can hope for the best at least. So my last question is about your week on the Twitter account, and I'm just going to quickly explain to new listeners to this podcast, maybe. So this podcast is one part of our Real Sciences Nano project, and the other part is a Twitter account which our guests take over for 1 week to show more of their research, and you can basically follow along and also ask questions. And I basically want to ask you, Chris, what are your rough plans for this week?
Yeah, so I haven't quite sorted everything out exactly, but my plans as of now are I'd like to highlight some of the work that's being done in my current lab because we have multiple different projects that are going on that are all surface science projects. So I'd like to highlight some of those, rather than just only focus on me, because I'd like to highlight our group if possible. And some of that work will highlight some of my previous work. So, I think that's my plans. So I haven't quite decided exactly how I want to do it, but that's what I intend to do.
Okay, cool. Is it a big group you're working in now?
No, it's a smaller group. So everyone gets to have some ownership over their project.
And you can have some already after 1 month, you kind of have an idea what other people are doing. It's not like, so big that you
Right.
cannot have an overview after the short amount of time, I
Yeah,
guess.
it's definitely manageable.
Okay, that sounds interesting that we are not only, getting to know you, but also other people's work and other scientists maybe. Looking forward to that.
Me too.
Before I let you go, is there anything else you want to say? Anything, that didn't fit into my question so far?
Not really. I think you covered a lot. Thank you for having me. I'm looking forward to joining you guys. I'm excited to be a part of the Real Science Nano program.
Thank you so much for speaking with me and for volunteering to this project. Thanks all our listeners for tuning in, and see you soon.